doing that, somewhere we have written that 85% of the single layer. You might have seen my, right? Yeah. It is not 100%, right? So suppose if I'm changing 20 kilowatt, it may give 70% of the single layer.
Maybe the velocity studies we need to do.
Yes. So this is what exactly the things are going on.
Thank you.
Yeah.
Thank you.
Thank you. Thank you. Go ahead, sir, please. Yes, sir. Griffin is very strong, very true. Great. Yep.
The picture of bulletproof or coat or whatever coating that we can use in graphene when we extract it out in other applications rather than
your ideas
than the aerospace or whatever.
Sir, your thinking is going in the very, very right direction. People are doing that. People are already doing that. You know, the graphene having the very high damping capacity. So damping capacity means the bulletproof shock absorbing capacity is very, very high, and people are trying to exploit the graphene for making the bulletproof jackets. Yeah. Okay. Thank you. Thank you. Thank you so much for the great opportunity. Thank you so, so much. Thank you.
Thank you, Doctor. May I call upon Dr. Sai for the next presentation, Indus Resonator, the wave-based wireless power transfer. Please welcome, Doctor.
Okay, so I'm not that big as a speaker before me or the speaker after me. So I'm fortunate to be sandwiched between both of them, all right? And I also have I really can appreciate both the fields because I know what he's doing, graphene. I've studied it when I was a PhD student. And out of personal hobby, I am half a geologist. So, and I'm more interested in dinosaurs and, those kind of things. But anyway, and I ended up being an electrical engineer. And this is Indus Resonator. As the name suggests, it comes from the river Indus. So that tells you about my geological interests. Because Indus is is older than Ganga River, and even older is Narmada River. So anyway, coming back to the topic here, can I change slide, please? Okay, so this is me. I'm Sai. I did my PhD in electrical engineering from Ulsan National Institute of Science and Technology, South Korea. My specialization is Zenek wave-based power transmission system, specifically designed to defeat Faraday shields. And why Faraday shields? Because, we encounter metal almost everywhere, whether industry, whether shipbuilding or shipping, right? And you require wireless power transmission to work through these places, and it is a century-old problem, okay? So I won the URSI Young Scientist Award for this. I was a assistant professor with the Indian Institute of Technology. Then I founded my company, which was based out of my own PhD thesis in South Korea. And then I was a professor in China for 3 years during the COVID times. So yeah, next slide, please. So anyway, I could raise about 1.6 million US dollars in South Korea for this, for the company. There were 3 companies which came out of my PhD thesis. The first one is Z in Ocean Technologies, where Z is the name of my professor's father and N is my father's name. SB Solutions, and then there is Sunny Wave. So I've worked with all of these things. Next slide, please. All right, so now that company is doing well and I'm out of it. Next slide, please. This is the outline of the talk today, a little bit of, of everything. So I'm not going to keep it like an official, very serious kind of conversation. It's going to be more like a casual way of saying it because this is a very boring topic. Next slide. So target areas, agriculture, logistics, and military for the drones and UAVs. You have industrial IoT, medical IoT, and soft robotics IoT. That's where you can also use these things. And then there is goal number 7, SDG. So you might be aware of this, where you want to use damless turbulent generators, and then you could use these wireless power transmission systems to, operate over large geographically, desolate areas which are prone to landslide and earthquake. Anyway, so next slide, please. So wireless power transfer started 130 years ago when Nikola Tesla in 1895 demonstrated in New York. And unknown to him, 2 weeks later, J.C. Bose in India, Kolkata, he demonstrates how to ignite a gunpowder across several rooms. So both of them were actually confirming each other's work in a way. And both of them tore off the patents. They were against patents. So wireless power transfer can be classified, usually before I did my work, wireless power transfer was classified only as 2 systems, near field coupling and far field coupling. But then I came up with something called the near field interface waves, and this is where the story of Indus Resonator begins. This is not my story, it's the story of Indus Resonator. So, the highest range achieved by inductive resonance coupling is 50 centimeters, and magnetic resonance coupling, which came from MIT, was 2 meters. And both these things operate on the principle of resonance. And resonance in electrical circuit does great things. For example, you can transmit a high amount of power over large distances. All right. How to explain resonance? In a marriage, a man's negative dominance and a wife's negative dominance, they cancel out each other, and then you hit resonance. Anyway, so moving forward, next slide, please. All right. So the potential, the potential of wireless power transmission, given the potential of the revenue and the finances, global scale, at a global scale, runs in billions of dollars. Okay. Even if we can capture through our technology commercialization only 1% or 2% of this, I think Professor Amia's dream of achieving $5 billion, that target will be near. So that's why this is important. Okay, there are 2 billion shipping containers worldwide, and all of them have to be made into a smart system, which can self-guide, self-control, and can be, operated. The operator doesn't have to intervene; it does self-correction of the things. So something like that, right? All right, and also we have a lot of piracy resurgent in the Arabian Sea now. So therefore, smart containers become ever more important now. Okay, next slide. Also, electric vehicles is a growing force. Now, 1 in every 5 vehicles is electric vehicle in my country, that is India. And they are all prone to one problem, that is battery catching fires. And also, when you have physical conductors, there is a possibility of short circuit, which will actually lead to catching up fire again, right? Unfortunately, vehicles and people got roasted in this process, but then that's okay. So that's why we need wireless power transmission, right? Next one. So a battery and power supply is present almost everywhere now. IoT, smart logistics, electric vehicles, drones. Now, there is a very big problem with IoT. Everybody is talking about IoT. It's great, yeah. They are talking about Moore's law once again, that Moore's law will, cause the IoT to jump up, right? But you have to remember, every IoT device is a sensor, and each sensor is actually driven by a battery. And let's say a 5-ton steel plant with an output of 5-ton steel every 6 months will require about 2 million IoT devices for Industry 4.0 to actually materialize. Now, 2 million IoT devices will be 2 million batteries. And every 2 years, you have to dedicate so many human hours to inspect, produce, move those batteries, replace those batteries, dump the batteries. Ridiculous. You don't want that. That's impossible. So I can at least address this problem using, batteryless electronics. I can directly power them using wireless power transmission. I can do the same with smart logistics. Drones, I cannot avoid batteries, unfortunately. Electric vehicles, I cannot avoid batteries. Okay. So what I can avoid, I will avoid. That's the line of thinking. Next slide, please. But now let's talk about challenges. Everything has a challenge. Okay. Wireless power transfer also has a challenge. When you talk about inductive coupling or resonant coupling, coupling-based wireless power transmission systems, they have to be perfectly co-aligned. If they are not co-aligned, you will see that power drops. As you can see, that's my hand anyway. That's also my hand there. I put a sheet of metal between the transmitter and the receiver. It'll block out all the power. This is called Faraday shielding effect, right? So, but the industry is full of metal. How are you going to, make sure that the transmission systems are co-aligned? Because if there is a metal in between, metal is opaque as far as I know. It's optically opaque in nature. So I cannot, there's no way for me to know how if it's co-aligned or not. And also Faraday shielding is taking into effect, so it will not work. Next. And then there is also another problem that when you have multiple receivers coming in, the peak of the resonance that starts splitting here, okay? This is very similar to how two pendulums are coupled through a spring, and if you have too tight a coupling, there will be two different modes. So this is what happens here too. Next slide, please. All right, 2013, okay? I was a student and young at that time, exactly 10 years ago. That was December 2013 at Ulsan's Hyundai Heavy Industry Shipbuilding Unit. I was taken there, I was shown this place, and I was told that you have to implement wireless power transmission system. We were 5 people, one guy just dropped out immediately as he saw this, because he thought it was crazy, it's impossible to do this. But then I had an eye for the ventilator ducts, because you're breathing, human beings are supposed to breathe, right? And if it's ship, there has to be air ventilator for the human beings and air ventilator for the IC engines, right? Because without them, neither can function. So I have a window of opportunity to transmit power through that. But then the problem is that the cross-sectional area of the ventilator keeps changing throughout the ship. So I'm hit with a classic problem of cutoff frequency, that if the area is smaller, I cannot transmit a frequency with a wavelength larger than that one, right? And then again, there is another window of opportunity, gaskets. Today, when you go back home, you open your refrigerator, just look at the rubber gasket which is there, which is used for mating and which is used for water tightening or air tightening the compartments. And then there is pipe and wire transit systems in the walls, where again they use neoprene gaskets. So again, neoprene is something which is transparent to electromagnetic waves. So again, I have an opportunity. So I had a crazy idea that how about converting the entire ship into a transmitting system, an electromagnetic system. And this is where this metal hugging wave concept clicked in my head. I didn't know much about electromagnetics at that point in time. Okay, but it just happened to me. So then I started the literature survey, that how it's possible. And my other teammates, they started with how it's not possible. So they were encountering how it is not possible, and I was encountering how it is possible. Okay, so that's just the perspective difference. Next. So I very quickly knew what to avoid. I knew that the perpendicular magnetic field to the metal should be avoided, because that's going to cause eddy current losses. Very clear, right? And then, so Maxwell's law, it says that if the electric and magnetic field are perpendicular to each other, so there will be if I have a parallel magnetic field, then I'll have a perpendicular electric field. And there is something which works like this, and it's called the transverse magnetic mode wave. Okay, TM mode wave. So that was the answer, that was the solution. So that was some encouragement. And then I came across several literatures which talked about, Arnold Sommerfeld with his theory on surface waves. Okay. It was a grand mathematical treatise. I couldn't make out anything out of it in the initial few days, but then we move on now. Next. So I came up in 2014, August 15th, with this idea that I can have I can force a perpendicular electric field to the metal if I can have a ground-backed impedance, and that's the visual representation of it. What you can see. Next. And then I realized this antenna had a problem. The problem was of the enough voltage headroom which was not there. So I remembered something I studied during my bachelor days about quiescent point in transistors, and I carried that lesson with me, and I thought maybe the same thing is happening, and it actually was happening that way. Next. So I also remembered while my work with ABB during 2006, 2007, that they were using, the engineers would use a counterpoise system. Counterpoise is nothing but a rat tail wire, which actually they tie to your own arm. And at radio frequency, the frequency is so high that your body now starts behaving like a conductor. So when you're standing on the ground, you're actually giving ground to the antenna system there. So this is called counterpoise. I remembered this. My colleagues didn't. And that's where I had the whole problem. Next. And then the first milestone was achieved on the 15th of August, Independence Day of both India and Korea. Okay. And so as you can see, this is a thick 80 mm steel block. That's the transmitter, that's the receiver. And here is my counterpoise system, which is a wire and a flat metal sheet. And I could transmit power across this 80 mm thick metal wall. And this was encouraging. Immediately, my professor declared about this, and the Korean media started coming into my university. My face started flashing on every other bus as a face of global Korea. I didn't want that, but that was a problem, because I knew very soon problem is going to come behind it. Next. Then the second milestone, and this was the best one. We went to India Heavy Industries, a Dolphin semi-submersible oil rig. That's the world's largest oil rig, by the way. And my Vietnamese friend, Quang, who was the only one standing after everyone else had left. Okay, he was the only guy who stuck until this point in time. I was inside this pontoon tank below the water surface, almost 8 meters down. And that day, this thing started working from there inside to there up there, and even at the helicopter deck. Just a single device. Until this point in time, people were using relays to communicate across each floor. They were not able to do that. But with this one, with a single device, it was possible. Everything was possible now. And the people who were there, the safety people who were there, present there at that point, they started chattering about this thing. And I immediately knew something big had happened today, which had not happened before. Those gentlemen had not seen it. I had no idea. And then, again, media galore. Face of global Korea. Okay. Now, this is where the entire problem starts. After this, I get URSI Young Scientist Award. I also get hired at the Indian Institute of Technology because my PhD thesis is submitted in December 15, and in February 16, I graduate and I join IIT Tirupati. And then, next. And then my professor starts his companies based on this PhD thesis, and then this controversies started coming up. And this is where the story's next part begins. And this is very melodramatic. So the main partially rational criticism of the system was cannot be simulated and no proven theory. That, of course, that was truth. Because I was trying to find a path of my own. It was not known to anyone. Okay? So I admitted immediately. I said, that's fine. EM emission may be high. So, all right, but they don't understand the system. That's why they're saying it. I knew that emission is not high. Current must be there in the metal. Again, And then just a pure guesswork. These are my favorites. It came from a professor, a well-known professor in IIT who won Patna Award from IIT Madras. Okay, but that I partially disagree with him because he uses a similar concept in his VLSI domain. It's called virtual ground in transistors. I reminded him that you are using virtual ground. I'm using another kind of counterpoise. He got angry. But anyway, that was a story for another day. And hence, I couldn't make it into IIT Hyderabad. That's how it happened. Then it was irrational controversies, which was counterpoise system is a false analogy. Such a thing doesn't exist. Actually, they forgot throughout 1930s, 40s, and 60s, US Army military and even ABB Corporate Research Center was using counterpoise system for their antennas. Okay. Cannot work in multiple receivers. Okay, fine, all right. Must be capacitive and no wave. Will not work under shielded metal zones. Okay, that was, but I had already proven that it works. Then there were personal attacks. Elaborate hoax, I didn't take it to heart, that's fine. There might be batteries. This is my personal favorite, and I'll show you what I did after this. Okay, Tesla cult in the academia. This is a very insulting thing, and I'll also tell you what happened. Right, slipped through the cracks in the academia. All right, next. Then here comes the boy that won the war completely, the Indus resonator system. So let me start by saying that any wireless power transmission system is a coupled RLC system, okay? And all RLC coupled systems can be explained by the spring mass damper model or a coupled pendula analogy. This is well known to everyone, okay? So these are the equations. I'm not going to bore you down with them. Next. So everything is accounted for. The masses will be your inductances. The resistance offered by these places which are tied can be given by the resistance, and the damping of the air can be given by capacitance. Voltage can be the input, and the output current is the displacement. Okay, that's fine. And the coupling between these two can be given by the spring mass constant. But what do you do about the ground? Nobody ever speaks about it. That's the most important thing, earth or grounding. So the ceiling, where you're tying all these two systems, the pendulums, is the ground. Same thing happens here. This is the ground here. But what happens if one ceiling is not exactly at the same level as the other ceiling? There's a difference in height. So there's a difference in the transmission of power from this guy to this guy. Same thing happens with this one. If you're grounding in a mobile receiver, have you ever wondered how the grounding is achieved in a mobile receiver? It's achieved through your body capacitance. So that is what we are looking at. And that's what the counterpoise was all about. And this is where the entire, answer to this problem existed. Next. All right, so this is more on counterpoise system, which I supported, showed them how this works, how Tesla actually built in his Wardenclyffe Tower an extensive network of ground. He went 60 feet below Earth to achieve zero resistance, almost zero resistance. And it's well known to civil engineers, by the way. Right? After a certain depth down, you're actually approaching towards nearly zero. It's never zero, but nearly zero. And then that's the counterpoise system right there. Okay? And that's the counterpoise system of ABB with which I worked in 2008. So I come with this answer. I looked at Tesla's transformer, open-ended secondary transformer. Open-ended secondary transformer means a very high voltage will be there and the current will be actually zero. This is the only point in time when there is an absolute quantity of zero. Okay, that's where it comes in, Tesla transformer. But Tesla transformer is quarter wavelength in nature. That means whatever frequency you're operating at, you will take 1/4 of that length to build your wire system, this wire, okay? So I changed this system because it has to operate on the ground, on the metal. So if I use quarter wave, then it'll become end fire helical antenna, it will start radiating and I'll not achieve my goal. So I had to shift towards lambda by 2, which is actually going to provide me with the correct kind of electrical resonance for the voltage headroom. And also it's going to create a virtual ground right there. And then it's going to drive the voltage of the terminal, very high, almost 2000 volts. And I could generate plasma at room with this. By the way, this is the only system which can also do that. No other system can do plasma at room temperature at 27 megahertz. So that's something, another feat, which I'm going to talk about later with other guys, not with you guys, I'm sorry. So the controversy one was beyond reasonable doubt was settled. It was possible to simulate this entire thing on, HFSS, which is widely used software in my field. So I had now the mathematical model, I had now the mathematical equations, 60 pages of derivations proving that how this thing works. Then this is the visualization of how the concept diagrams. This is the mode which is generated. This is the transverse magnetic mode. I'm not going to bore you with that, but I'm going to tell you that when you drive voltage through this secondary open-ended transformer, the top tip will have a, let's say, positive charge. And in the metal, there will be a counter charge which will be generated. And there will be two electric fields of line which are going to meet exactly at the metal and air interface, just like lightning strike. Lightning strike happens, charges fall down, and the charges also come from the earth. They both meet at a point, and that's a neutral point. That's how the metal is going to be neutral. This is called localized charge oscillations. Next. So you can see this can work through the shield. Now my transmitter is inside the shield, okay? And my receivers, they are receiving power through multiple metal, obstacles, not aligned at all, okay? So all problems have been solved, multi-receiver. And this is the beginning of the exciting phase of my life. When this happened, this was the most beautiful moment of my life. Next. Okay, this was one of the numerical model equations I came up with after 64 pages of derivation. I'm not going to bore you with that, but all controversies are now settled. It exhibits a very low decay rate. So that means if I go along the metal, the decay of the field is now very, very low. So I can go really, really great distances to transmit power on the ship, okay? Or the pipelines. Next. It can work under the shields, definitely proven through field emissions, okay? And this is the field emission report generated after testing on a NARDA field test analyzer, which is actually accepted analyzing system. As it turns out, it's way below the accepted limits. So that's fine. So as long as it's below accepted limits, everything is fine. One particular director of an IIT, he thought that the field emissions will be very high, but then it turned out it's not so. Next. Okay, so this is also another controversy debunked, that it is a capacitive system. That's also done. This is a video, so you have to jump. All right, that's a video there. They said there are batteries. One reviewer said there are batteries. So this is the video, I sent it to him. Hello? Hello? The transmitter. And now we are going to the receiver. And that's also hollow. There are no batteries anywhere. Hello. So after my article was accepted, that reviewer contacted me and he said, stop insulting me like that. So, but then he started it. I was just returning the favor. Next. Now this is a definitive proof. Oh, wait, come back. Yeah. Now this is the this is a video. We are going to place this camera inside this box here. That's a halogen lamp. I don't use LEDs because LEDs don't require high current. It's the halogen which requires at least 2 amps of current. And that's a definitive proof that it's a wireless power transmission system. And now we go. Field is on. Power on. As you can see, this is very difficult to achieve. And the president of the MTTS Society, IEEE MTTS Society. After looking at this video, I sent it to him, George E. Ponchak. So he threw out a challenge. Yeah, it's okay. Yeah. So the president of the IEEE MTTS Society throws out a challenge at a global scale, at a global level, asking any other WPT researcher to do what it did inside the shield. Nobody was willing to take that challenge. That challenge is still open to this day. Only Indus can do that. Next. All right, this is the video proving that there is no current in the metal. Okay, so there's this question asked whether there is any current flowing into the metal. This is the metal. Answer is. Remember, I told you at RF frequency, your body is the path to the ground. So if there is a current there, it should actually start glowing even with one LED, LED on the thing, right? But it doesn't happen. But there on the receiver, it happens right there. Not on the metal, on the receiver or the transmitter. I can get it. But if I do the same thing here, doesn't happen. Nothing happens. Right. So this is how I defended my work through a series of videos. I think nobody else, very few people have to do such a thing, but this was the thing. It's exactly like Tesla transform. That's what happens. So this has become a kind of neutral ground point. Next. So yeah, this is multi-receiver. Next. Okay. This is our. So this is a long distance transmission. Okay, here's our maximum we can go right now is 16 meters. So here we have 15 meters. Here we have 16 meters. That's it. Actually, it's a little more than 16 because the line twists and turns around, so quite a bit. Now replace those receivers with a series of sensors and imagine how I can power all those sensors using this tech. That's it. Receiver 1. Receiver 1. Receiver 2 there. And now I've actually started working on a modified system, and then pandemic hit everything. And since then, I have not worked in this area. Now I'm a super administrator. Thank you. If there are any questions, please feel free to ask. Yes, please.
I just need to, I'm enthusiastic to know a single thing or a basic thing regarding the efficiency. Like
89.91%.
89.1. Okay. So it's really a good work. We should appreciate that. So
Actually, that efficiency is only for one transmitter to one receiver. But if I increase the number of receivers, this is a near field system. So the efficiency jumps up to 92% overall efficiency.
Okay.
So you have to increase the number of receivers to have more efficient thing. Because remember, the power is all across the metal surface.
Mm-hmm.
So the more the number of in principle, you should be able to achieve 100% efficiency. But then that will not happen. That's never possible.
So
We don't have enough electronics to do that.
There should be some energy loss, right? So in the future, can we expect something like charging our cell phones?
Oh, I'm way past charging cell phones. Charging cell phones is done by MI people.
Okay.
I don't do that.
Uh-huh.
I'm talking about industrial IoT.
Okay.
This is very different from your consumer electronics. Because for consumer electronics, everything is already very well done already. So there's no point in me working on it.
So you're not interested in
Yeah, it's already done. 95% efficiency is already there. It's as good as a transformer, 95% efficiency. So that's what, you don't need it.
That's great. Keep working. Thank you.
Thank you. Thank you.
with this. No, no need.
Thank you. Honored. I'm honored.
Good morning for the gathering.
Morning.
Great show.
Thank you.
Actually, I thought my students have missed the show.
Okay.
It was quite inspiring.
you.
Okay, from our side, we are all our folks are from computer science. So since we are working on, and also I saw your background from China and as well. Do you have any supports, structures or framework for green technology?
No, I don't.
Okay. Any funding mechanisms from China?
Not possible. Not that I can think of. I think Professor Amia is already on it.
Actually, he is a part of the research as well.
He is very well equipped to do that. More equipped than me.
A final question.
Hmm.
Is there any funding mechanism from NZ or Sunnywave from your side as an entrepreneur?
Sunnywave, no, they will not. But I know a few venture capitalists
Uh-huh.
who can support a startup, a late stage startup or an early stage startup. That's always possible. They are based out of Singapore. Maybe
Great.
you know. They are a plug and play accelerator.
No. Then getting funding mechanism from Singapore is a high task.
No.
right?
See, my funding mechanism is not at research level. I can't do that.
Oh, okay.
I'm not equipped to do that. But I'm actually equipped to, and very well equipped to bring funding
Uh-huh.
for you if you do a startup.
Great.
That's possible.
Thank you.
Thank you. Okay. Yeah.
It's the industrial discovery on wave transmission power. How do I make money out of this? How do I know I've seen this. Can it be commercialized so I can make money, or we can make money out of this? Maybe a railway line
Yes.
with a metal.
Yes.
The train moves
Yes.
without any power lines and all those. Is that possible?
I'm not aiming for such a high power
Uh-huh.
because we don't have the electronics to do that. We are not ready yet for that. But we are definitely ready for doing IoT, powering up of sensors, IoT sensors and things like that. That is possible. Your oil and gas industry, your entire pipeline is there, right? And you need to ensure that there is no contamination in the gas or oil or even water lines, water pipelines, right? So there also you would run these waves to power all those sensors, and it can work through water, by the way. So it's not a problem. Yeah.
Possible.
Yeah, possible. But you have to give me $1 million to make it into a reality. That's how much fund I need right now. Okay, if no other questions, then we can move on. Thank you so much.
Thank you, Doctor. That was an amazing presentation. May I call upon Professor Triloknath Singh for the presentation Slope Stability Analysis on High Hills. Please welcome, Doctor.
So, can you display, please? Okay, before we can start. I think this time is very important. So thank you for giving me this opportunity to express some of the things. You have seen the two wonderful lecture and speakers in front of you, those who have done and excel a very good research at the laboratory. I'm not a person who can work in the laboratory. I always think that the nature is the biggest laboratory for me. And that is the reason I have chosen this topic, the slope stability analysis is high hills. And this problem is not addressing only this one place or one site. It is across the world we have the natural disaster. And this landslide, rockfall, avalanches, flash flooding, these are the common phenomena across the world. And you know that people are losing their life in the different parts of the world due to these kind of the problems. I remember 7 to 8 years back, I came in the SARC representative in the Malaysia, in the Kuala Lumpur. We have this discussion, and that time one of the professors has shown a site where 8 buildings were been collapsed due to because the foothills of the mountain, and then one night it has been slided down and that damaged all these people and people have lost their life. So these are the problems are persistently you can experience, you can hear, you can go to newspaper and everywhere you can get it. So I wanted to just show you some of these small things what I have done in the terms of this taking in the high hills. Once you can say in the particularly in India or Bharat, then automatically the name appears in the Himalaya. Himalaya has a longer, you can say, extension starting from the Jammu and Kashmir, coming up to the Arunachal Pradesh. All across that we have the high hills, and these mountains are known as the dynamic mountains. It's a young mountain, it is still growing mountains in both in the horizontal and the vertical direction, both that has been reported, that is uplifting as well as shifting. Though the rate is not very, very high, but yes, that has been measured. So next slide, please. So what I wanted to address, there are many problems, natural problems related to the slope stability, mostly the erosion, rockfall, earthquake, external loading sometimes because everyone is going for their development, particularly in Bharat, we have a lot of development work connecting the people from the remote area up to the mainland. These things are happening everywhere, and these things create sometimes this problem. And these problems are by the some of these figures can just show you how it is happening and how this landslide is taking place. Just you can see this how narrow road, this we wanted to expand it, and while doing the expansion there is a possibility of any kind of this failure, and this failure is persistent and is very well visible that the complete road is blocked and the huge debris has fallen down. So similarly, we have a number of places. How much time you are giving to me? No. Okay, so I will not bore you much because after 2 interesting lectures, I don't want to make any disaster particular in the mind of the people. Okay, so these are the things which had to be addressed if you want to save and secure life of this any person or any commuting person on that one. Next, please. So people say that whatever the investigation you can do, whatever the advancement has been made so far, but still the natural surprise one cannot avoid. Just like our human body, whatever the pathological test you can do, but still sometimes something will be not been detected. It has been not been diagnosed. And then the experience and expertise of the doctors comes into the picture. And similar way in the nature, the geological surprise can be anticipated. One can feel out of that. But what will be the solution? That needs some time to understand. What people say is that if you want to understand the earth, then one of these famous authors, Arthur Holmes, he has written his book, and the first quote he has given on the top, that if you want to understand the earth, you can sleep and dream over it. Then only you can understand. So more closer to the problem, the more appreciation and anticipation one can make. So these are the some of this, you can say, the surprises in the terms of this rock fall. Then you have the mass movement, this block. Then you have the sinking problem, particularly our eastern region of the Bharat. You can see the Arunachal Pradesh, then the Mizoram, the Shillong in the Assam area. All the places there is a sinking of this material. Even in the mining field also, we have the sinking is one of the. Once you are doing the underground mining, then if you are extracting some material, there is a possibility of sinking, and we call it just subsidence. Even in the road, you have seen some kind of subsidence. It may be subsurface, it may be the surface, it is a larger sinking of that. So that will be possible in the collapse of the thing. So that will be the sinking zone is also important to make the road safe and secure. Next, please. So once you are designing any slope, either by the mining engineer or the civil engineer or the engineering geologist, we have to keep a certain parameters into the consideration. And mainly I can say it is a very broad because there is a number of parameters. The parameters here, you have to understand the geological details of the particular site. What are the rock types? What are the geological discontinuity? What are the defects in the rock? Their orientation, the slope geometry, how it is sloping from the ground, water conditions, whether the flow of the water, or it is a wet material, or it is a dry material. What kind of the filling material need to be the two rock blocks? What is a calcareous? It is a siliceous, it is a perigeneous. So that makes this rock ability for standing with time, what we call a standing time of this. So these are the things is required. And also the method of excavation. Whether you are excavating by just, people said about the plasma cutting, or electric detonator or electronic wire system, giving a high energy, high temperature for a shorter period of time, then you can cut. Laser beam cutting. But you know, it is not a small block, it is huge. The length will be maybe few hundred meters, the height will be the few kilometers sometimes. So these cuttings are not possible in the nature. What is the cheapest way available till today? A research, you can better go by the blasting method. The moment you said the blasting, people are afraid with this word across the world. And I think they are right in thinking. Because Noble has not reported his findings about the explosive recovery if we know that human being is going to misutilize for killing himself. But still, that is the old story, whatever he has given. So you can do the blasting. Once you can do the blasting, then whatever the slope which will be standing, that also suffered due to the wave generated through that. All the wave with the interference wave, PSL wave. So everyone had the different velocity. Everyone had the different frequency. And finally, we have to save the structure, a standing slope, as well as the habitant near that. So once you can do the control blasting and monitor it, that it will be within the safe limit. Because any vibration will be not going to disturb. Because once you are sitting in this room, we are walking, there is some vibration. But that will not going to damage this building because this has been made of the higher vibration level to sustain the higher level. So these are the excavation methods. And once you have the excavation, then we can go for the certain stabilization method. Next, please. Just you can see the conditions of one of the sites in India. A huge block has been fallen down and it is disrupted. You can imagine if it happens to some vehicle or some human being, what will the condition of this man and woman which is passing through that one. So these are the conditions, and you can see the discontinuities existing in the rock. It is not a monolithic material. It is not a heterogeneous material, but it is a material which has a number of defects, number of fractures, number of discontinuity. And this water is one of the another enemy. You can find water is a life supporting system. It is very important for everybody, for human life. But for rock, it is one of the first enemy. So the same thing can be the life supporting, and the same thing can be used as just like a disturbing the life. So one of the things which you can see. Next, please. Just you can see what I said earlier. Okay, if it happens, and this happens in this Pune Expressway, the road which is the lifeline which is connecting Bombay to Pune is very busy road. Lakhs of this vehicles are moving every day, and it happens on the same road, and you can see the vehicle condition. And I think I should not explain much about the tragedy, but you can appreciate what will be happened, and by the figure I can think you can make out a sense that what happened to the people who are inside this. Now, how to address this problem? Because we cannot stop going, because movement is life. If you are not moving, your body is not moving, it means you have gone. So similarly, we can keep the people should move. So we have found out certain solution. Next, please. So you can see some of this area, this one of the another area, I have taken some of this example just to address this problem. One of this area is known as Sonbhadra. It is the mostly a rock is little bit harder in terms of, because it is a very good, you can say this sandstone. And many of the monuments, if you happen to visit in Varanasi, which is one of the very famous city because of this Indian Prime Minister is representing that constituency. And he has made a remarkable renovation in all about the Ganga Ghat. So all this, you can say this new and old ghats has been renovated using this kind of this material. It is a very useful material, very good building stone. So all the red color flies high strength, about 70 to 80 megapascal, having a very good sense of this chemical composition. Is a silica is about 90%, so very resistant to the water, very resistant. There is no wear and tear in the longer period of time, and many of the forts has been made on that area. So people wanted to connect Varanasi with this power capital of India. Many of you think about Delhi, it is not Delhi. The power capital means a huge power is generated in a very smaller area, and that will be called the Sigrauli. This northern coal field, where this huge coal field, we have 300 billion tons of this coal production. As huge machines are working. So we wanted to connect from Varanasi to that place is a 220 kilometers. And it will be all ghats of this hilly region. You have a different U you have to form, and then you can climb. So job is given to break several U and make a one U. And what we have done we have done this slope stability analysis because you require a lot of cutting is required. Next, please. Just you can see the conditions of that area. And I think you can appreciate of this location 6, what will be the height of that. Once you are trying to make a 1U, what will be the condition? And these conditions, and then the possibility, in some of the figures you have seen, my ex-colleague, those who have worked with me for their PhD, but now they are faculty. So you can see this, how the discontinuity play a role. Can I have a pointer, please? Yeah, no, this is pen. Okay. Okay. If I can put it here, you can see this discontinuities. These are very difficult to control. And this you can see. This is the height you can appreciate, and you can see almost vertical slope. It's almost vertical slope, near to 90 degrees, very high. Next, please. And these are some of this parameter, the slope height which have to address. At least you can take the 10 to 15 meter. That should be the stable. These are the dipping conditions of the joint and defect I said. And these are some physical parameters which required to be model. We have done it in the laboratory. We have brought the sample. It is very tedious work. And then you can see this randomness of 3 plus random joints. So more number of joints, the rock is more vulnerable, more weak, and likely to fail early as compared to the similar rock, but having the less joint. So rock type will be not an indicator only for the slope stability. It will be only giving you some strength parameter. Next, please. These are some of the tests we have performed. Those who are from the civil engineering and mining engineering background, they can only better way appreciate. For others, it is just like you can say some kind of the test. So these are the tests we have conducted. We wanted to know this elastic properties of the material, what is the Young's modulus, what is the Poisson's ratio, what is the modulus of rigidity, all can be determined with this laboratory. And we have the test. You can see this, how this rock fail once you can load it. Okay, next please. This is the test which we have performed in our laboratory. Understanding the rock, once the rock have the confinement, because you may ask that the slope, the rock is exposed. So one face is, once there is a loading, one face is free and other rest of the face are confined. But there is a situation when the all around that this rock is confined. And what will be the strength? That will dictate the stability of that material. Otherwise, there is no way. And this test is very, very pertinent once you want to start any kind of this underground excavation, either for oil storage, underground building, underground parking, anything about the hydropower generation. So a lot of activities are going on. So these tests are giving you some idea about this, how this rock will respond, behave during the triaxial condition. So this is the this rock sample is within this cell, and power is given all surrounded. We have this oil, and that will be the providing the pressure from here. Just you can see, and then the test will be conducted, and there are some sensors which can give you some data with respect to the time, how this strain is developed during the normal pressure. Am I clear? Okay, thank you. Next, please. Then we have started certain kind of this numerical simulation. Please. Just you can see, this is the very first method, the very simplest method, which has been started in 1900. 1900, when the Mohrs has given a first solution for this slope stability, and thinking starts. And after that, Mohrs and Coulomb has value added, and they say, okay, tau is equal to C plus A into sigma and tan phi, where the angle of internal friction of the material. And that's how the failure criteria has been started. But I salute these mechanical engineers who have done earlier this kind of failure mechanism for the failure criteria defining the material. But under the compression mode, the first time it has happened by the Mohrs and Coulomb. Then the Mogi has come up this long way to defining this failure criteria. And then we have the continuous Barton and Barnes model, then Chaube and Barton model. So plenty of model, 2025 model. So we have started from the scratch because the most available, most accepted, and most known criteria that is limit equilibrium. Next, please. And then we come to the FEM model, finite element model, because this is good. Limit equilibrium is always good once the material is mostly homogeneous material, weak material, where there's possibility of formation of the slip circle, and then we can go. But once you have this material, which I have shown you earlier in this rock, then I think the rock has been it can be divided into maximum possible sizes, geometrical sizes, and then we call it a mesh, and give the property of each node, and then try to see in holistic way. Here you can get the factor of safety, but here you can get a lot of information about the stress, strain, displacement, all these things at the different point and different values, and then you can see what is the overall health of the slope. Next, please. You can see this is the 2D model, this is the 3D model, and this is the mesh which has been generated. I told you this, all this has been discarded, which is not possible in doing in this field. Next, please. So I don't want to go for this how it works because it is well known to you. Next, I want to highlight the result of the finite element method. So you can see that all the constitutive model has been made, mostly the partial differential equations, and we have used the Mohrs-Coulomb criteria as a failure mode, and second one will the Hawk and Brown failure criteria for the understanding the failure mode. Next, please. And you can see this is the lines which indicating that rock has been a tendency to move like that, and you can see this stresses. The different color shows the different value of the stress, which can be, I think here it will be coded, and you can get the factor of safety of 1.02, and it will be in a static mode. It will be a static mode, means there is no intrusion of any kind of dynamic wave. There is a movement, there is an earthquake, all the things. So 1.02 is not acceptable as a stable field, though numerically it is stable. Next, please. Now you can see this velocity vectors, the tendency of the move. So this is the zone, this red one will be zone under the influence, and these are, you can say in the other language, layman language, is a cancerous field. We have to remove this tumor or rectify this tumor to make it a normal tumor. So this is the things which we have plotted. Next, this maximum velocity vector has been shown. Now you can see this appreciated more in this one. So you have UDEC model 7.0. It is a, I think one more version has came, 7.5 normally. So whatever we have done it by this one. Next, please. And then you can see here how this will the waves and how the peak. So this is the most dangerous area, and with different events, means all along the slope, how the waves will be responding once you can introduce certain kind of dynamism. Next, please. So we have done all these, and then we have provided certain solution. Next, please. So this is the, again, what I told you, the another failure criteria we have used, and you can just compare the result. Next, please. Here you can see what will be happening. This is the another side which I have shown you the 4 figures. And out of that, this is the another side is a more critical. You can see here the disturbance at the boundary conditions also here. And these are the, again, but it has a higher factor of safety. Earlier, if you remember, it is 1.02, it is 1.85. So quite a strong and efficient rock. Next, please. Okay, so critical stress reduction factor will be 1.8. Factor of safety is 1.85. Next, please. Even though there is a factor of safety is 1.85, but still there is a small pocket of the concentration of the stresses within the rock body. And that has to be checked from time to time. Otherwise, today, the things which is stable, particularly in nature, tomorrow it may not be. Because any change of the external factors may lead to some kind of increase in the concentration of this strength, and that will be a stress, and it will be the strength will be reduced. This is the ratio which dictates the factor of safety. Okay. Next, please. Next, just you can see this another accident. This is the near to Bombay. There is a call as a Kalyan area. This outer skirt of the Mumbai, and this is the road which connects to Raigad district. Very important road. This is the lifeline for the Bombay. If this road is disrupted, half of the Bombay doesn't have the vegetable and milk, because you know Bombay is a rich place, doesn't produce anything. There is no vegetable, there is no milk, and these are the feeding lines. And this accident happened at 4:30 early morning. A truck full of the vegetable was passing through that, and this boulder hits from the top. It was a rainy time. You can see these rain conditions, how much flow is coming. It's a high hill. One side is the hill, another side is the deeper valley, gorgeous. And it is an imagination looking through the person, the driver and his attendant. It was so high that automatically his door has been opened and he has gone like a football to a 25-meter away and just sitting on the tree. Just gone, and just like you can see somebody catch him. So he was putting there, having a lot of injury. Unfortunately, the helper, he was just like a sandwich between this. And this body has been fragmented in all possible things you can think. Nothing happened. And after that, we have been called. That time I was in IIT Bombay as a faculty. 6 o'clock, chief engineer called. Send your team immediately to this ghat. You know, this Bombay having the late night life. And people doesn't like to be early. Somebody can knock the door and say, get ready and go to the site. That will be very, very difficult. So I told my wife that I am going to that ghat with my team. She is also worried what happened. But anyway, I have moved and we have seen the condition. And you can see the size of the boulder by looking through the person of the average height of the 5.6 feet in the height. And you can see this boulder size and the machines has been read. Now we have the problem how to address this, because this road has been blocked, has been removed, and then you have to make a stable condition here, because that this area is also connected with that time the PWD Minister of State. So if any road is going to the minister's side and is a minister of the PWD, Public Works Department, road is coming under him. So he told that immediate some solutions should be provided, and we have done some work there. Next, please. Next slide, please. You can see this is the road. This is the height of some of the height, not complete height. And this is the range condition. And this, under this, we have to work and provide the solution. Next, please. Okay. So what we have done, I will show you later on a little bit. This is the another study, the Sangla Chitkul Road of the Kaimur, Himachal Pradesh. So you have a small journey starting from UP. I have taken you to the Maharashtra. Now I'm taking you to the Himachal. So the virtual journey of the rock types. So next, please. So I'm not going for this geological setting. It is a too typical. And you can see these conditions of the rock. And this is the road. And this road is very, very important because from Himachal, if you want to go to this China border, we have the single road. So used by public, used by the military and all for all safety issues. And you can see the condition of this discontinuity here. You can see here. We are trying to measure some of the parameters, mostly the core geological parameter about this joint orientation, joint inclination, joint persistence, joint filling material. All these parameters is crucial for designing. Next, please. Again, you can see this using the model. Next, please. And you can see this model has been prepared. And normally, it gives you a very fair factor of safety of 2.1. But still, there is a failure in this region because that failure is not a landslide. This failure is due to the rock fall. The rock fall is a localized failure of the rock, and rest of this rock will be just like you have a fracture in your whole body. So whole body is strong, but that part you have to make it operative. So similar kind of this rock fall. Next, please. You can see this maximum shear strain, the measurements, all is gone. Better not to go for the numerical value, but you can appreciate this physically what is happening and what kind of the disturbance is there. Next, please. This is the total displacement along the slope distance. So earlier very low, but slowly you can reaching more than this. You can say this 0.5 meter maximum. Next, please. Again, there is a model which you have used for the plasticity model here, that the cohesion value is 10.36 megapascal. Next, please. And you can see this entire scanning of the slope, how it looks like, and how this all color will be giving a certain kind of the value. Just for better appreciation, you can see the higher and lower value here, and you can get this value. And then based on this, what is the purpose of this? To provide a certain kind of the solution for the stability of the rock and making the road safe and secure. Next, please. This is the another site where this is the road. This is the road, and this is the slope height. Next, please. Just you can see, this is the another parameter, the displacement we are trying to know. All along the jointing parameter, we have the problem. Next, please. You can see the situation here, the field situation. What is the field? What is the values? And what is the slope looks like? This slope, 65-degree inclination. And the rock type is epidorite. It is one of the type of rock. And these are the parameters. Next, please. Once you can make a slope, then you can see this is the possible failure zone. This one. Next, please. Then you can see this is the another model. Why this is the disturbance all along the slope and how vulnerable it will be. It will be likely to fail because the factor of safety is coming 1.1. Next, please. You can see this dry condition. Why earlier I talked to you the dry condition. Once it is because in India you have the variable season, the extreme rain, extreme hot, extreme cold. So this material suffer once we have this high rainfall, and then this total rock is saturated. And once it will be saturated, then what will condition of this one? So this is the dry condition. 1.68 factor of safety. The factor of safety has been reduced. Once you have to take a 3D model, this is the 2D model, and these are the things which are happening on that one. Next, even this figure, earlier figure will show you that whether I can use a 2D model or 3D model. 3D will be better appreciation and understanding about the rock body as compared to 2D. 2D is a plain model. And that is the reason you are getting even 3D, the factor of safety is different than the 2D. And these are the, you can the saturated and the reduction of factor of safety. You can see this water. That is the reason I told you the water is the enemy for the rock. And 32.7%, somewhere 23.6, 32.7, again 32.4. So these are the reduction in the strength of the same material once you the water saturated. And this is the reason we have to drain out and not allow any water within this slope. Next, please. This is the another side where earlier, if you remember, the 65-degree slope. Now, the other rock, once you can proceed toward the road, this is 75%. And this is the road condition. And this is the rock. Next, please. This is a very hard rock, quartzite. And just you can see the similar treatment we have given for to understand that one. Next, please. You can see here 1.42 factor of safety. And this is the 0.94. So this whole mass is waiting to slide. Next, please. Again, the similar things we have done for the same site, and you have the dry and saturated condition. And you can see the reduction in the factor of safety due to the presence of water. Next, please. And these are the some of the result. So again, the reduction you can see in the saturated conditions, the factor of safety drastically reduce. The slope, which is 1.42, become 0.94, and 1.49 reduced to the 1. So they are all unstable zone, and we need certain kind of the treatment of that. Next, please. Oh, then we have done some kind of the probabilistic analysis. Normally, engineers do it. They using a different kind of this model. Mostly the Monte Carlo simulation model has been used, and then we can find out what will be the factor of safety and that. Next, please. Just you can see this one of the model here. The histogram of the factor of safety less than 1. These are the regions. The other regions are safe. So that what is the purpose of doing all these things? The purpose is to give the treatment wherever required, because it is a very costly affair. The whole slope cannot be protected by wire mesh or these rock bolts, or you can using these barriers. All is a costly. Even 1 meter change in the barrier height will be counting about few crores change. So I think the chairman has already given you the clue how to convert it to in dollars. So you can change. So these are the things which can be. Next, please. Here, this is again the sample. These are the difficult area which we need certain kind of the support. Next, please. And you can see a scatter plot of this cohesion, means cohesive strength of the material, because factor of safety, we have the cohesion, and angle of friction is very, very important and crucial parameter. So that's why losing the cohesion means losing the strength. Just like it is a frictional property, I can say. And everywhere, this work of any of this engineering material can be understood by the cohesion value once you want to the application. And most of the footwear industry are using in a very nice manner, providing a different type of grip so that there is a cohesion should not be zero. There is some cohesion. Next, please. This is the convergence plot of the probability. There is a 5.2% of the probability of the failure in one area, and mean factor of safety is coming 1.99. So in some area, we should not worried about anything. Let them live like that, and some treatment is required. Next, please. So what I have tried to do, this is the in concluding all these things, because I have been given a half an hour time earlier. So what I wanted to convey to you, that any slope stability problem can be taken in a holistic manner. Don't use a single type of the solution. you have to take a different test, means like a different kind of the model. Start from the limit equilibrium, go for the finite element, go for the finite difference method. Try to see where you are getting a most vulnerable things, and accordingly, and then we can plan for the barrier analysis. So we have started this work at IIT Bombay, and happy to inform you that we have designed the world highest barrier, 10,000 kilojoule barrier in Malsej Ghat. And that was the first thing that has been designed by India, not by me, my team, but it goes credit to my country that they have given this problem and we have solved. Bombay-Pune Expressway, we have given the solution, implemented one by God grace. From last 10 years, the area which was protected by our design is safe and secure. Nothing happened. Mata Vaishno Devi is another area where we have worked and pilgrims are safe. But there are many challenges which we have faced across that one. But it gives us a pleasure and satisfaction that something we have done for the society with our research work. So thank you very much for giving me the patient hearing, or if you have any question, query, I love, and always I think that the questions gives us some kind of a strength to think beyond what I have think on. Maybe as a researcher, I have a jaundice eye, so you can give me some suggestions so that I can remove this jaundice eye and see if this is your eye. Thank you very much. Can I give my?
That was a wonderful presentation, sir. And the data are more clear. And actually, I'm from flow analysis, not good in the structural analysis. But I'm curious in FEA, the software you mentioned. The geometry you showed 2 models, right? For the slope geometries.
Three.
Okay. That is taken from the real. So you have measured everything. And
Actually, just a very good question. And this is the gap I have kept. Okay, the reason is we have taken the slope profile using the LIDAR survey of that area, and similar profile with a certain smoothing is required as a modeler, you know. You cannot give any geometry until unless there is some equations of that geometry, either rectangular, triangular, a square. But if I can do a zigzag boundary, then solution will not converge. So we have taken this profile using the LIDAR survey. Now we are doing the drone survey to taking, because in such a high hills, it's hard to send somebody at your own risk, that if they're fallen, there's nothing. So we have used that one. And then we have done this profiling.
the number of grids, how many number of grids you have used for the number of elements you used for the mesh? What type of mesh you are used?
Mesh is mostly I have taken based on the problem, because once you can see the jointing parameter, once it will be having the 2 discontinuous so you have the interaction, then
Triangular mesh. So the notes you will correct during the, but I didn't see it. No, actually, I have used for the flow analysis almost 20 lakhs of number of elements I will use for the flow analysis. But from the results, I can see the grids are very limited. So that's why I'm asking.
Because you are working in your own model in the laboratory. I told you my laboratory is nature, and nature dictates me that what kind of the geometry and what kind of the grading and meshing I should use.
Thank you, sir.
Okay.
Clear from
Any
my
other
side.
question, please? Yes, please. You take a mic, so it's louder.
Am I audible, right?
Yeah, yes, sure.
Okay. So I'm asking, why can't we scan the rock and make it a solid data, and then we can analyze in the laboratory itself? We can use geomagic tools. Maybe you are aware, right?
Okay.
Are we using that one in the IIT?
Yeah.
That's my question.
Okay. Thank you. It is a very progressive thinking, and I must salute you for this. We have used, because you see all these parameters by the scan, we cannot do the justice to the model, because suppose there is a strength of the material, crushing strength, means how much compression load it can take if they vertically load it. If you can do the scanning, you can get some kind of the imaging about the presence of the mineral. Case on the mineral, you can think about the strength probability. The silica is higher, a strength will be higher. But there